All right, so this is our evaluating limits analytically day 2 lesson. So we're going to see some more trig. As you can see right here, we're going to learn some special limits and then see how we can apply those properties in some more creative ways to solve some more challenging limit problems. Okay, so this first one's going to ask us to figure out what the limit as x approaches 0 of sine x over x is. So remember I said that your first line of defense on a limit problem is to do direct substitution. So we're doing the limit as x approaches 0. We're going to plug in 0 for sine, okay? And sine of 0 is 0 on top. And then if I plug in 0 on bottom, I get 0. So it's 0 over 0. That's our indeterminate form, which means we have more work to do, but there's no algebra that I can do here. I can't factor or multiply by a conjugate or multiply by a denominator on top and bottom. So none of those things we learned about yesterday work. So we need something else here. All right. And so we're just going to investigate this on the graph. So grab a calculator or log on to Desmos and graph this function and then just make a guess of what you think this limit equals based on what you see on the graph. So I'll give you a minute, pause the video to try that, and then come back and see how you did. All right, so I'm going to pull up my calculator here, and I am going to type in control divided by sine of x divided by x. There's what our graph looks like, and if we're doing as x approaches 0, it's looking like the answer is 1. That would be my guess. Okay, so a sketch of this, it's going to pass through 1 right here. It's going to kind of go like that and like that. All right, so I think the answer is 1. All right, so we're going to do the same thing for 1 minus cosine over x. And so again, if we do direct substitution, cosine of 0 is 1. So it's 1 minus 1, which is 0 on top, and then we get 0 on bottom. So we're in indeterminate form. Again, there's no algebra we can do here to figure out what this is. And so we need to graph it and see what the graph looks like and decide. So once again, plug this into Desmos or your calculator and take a guess, and then unpause the video and see if your guess was the same as mine. All right, so I'm just going to tab here and I'm going to arrow back up to that graph, and I'm just going to change this function out, 1 minus cosine of x. All right, so as x approaches 0, that's right here. It looks like cosine, it looks like this function is approaching 0 as well. It's going right through the origin right there. So this kind of goes like this, like that. All right, so I think the answer to this is 0. All right, and so remember what I told you, when you get 0 over 0, that's actually signifying there's a hole in the graph right there. So that's what's happening. There's a hole in this graph, and there's a hole in this graph right here. Okay, but the limits are what they look like they were. This limit's equal to 1 because it's approaching 1 from the left and the right, and this limit's equal to 0 because it's approaching 0 from the left and the right. These are special properties, special trig limits you have to know. So these are two you just have to memorize. Okay, there is a nice proof of sine of theta over theta that uses the squeeze theorem, which we haven't covered yet. We will be covering that in our next lesson, I believe. And so after we cover that, I'll point you to a place where you can see that proof. It's pretty nifty way to prove this geometrically and algebraically, which is more rigorous than just looking at the graph and saying, hey, it looks like it's 1. All right. And so this one is equal to 0, and you just have to memorize these. All right, so now we're going to do some problems where we apply these properties. So our first example is the limit as x approaches 0 of sine of 5x divided by 5x. Okay, so we have our x approaching 0. Notice that both of these limits, the theta is approaching 0. That has to be the case. If your theta is approaching 1 or infinity or pi over 3, then it doesn't work. Okay, this is only for a limit where your variable is approaching 0. Okay, the other thing you're looking for both versions is that your theta inside the trig function, so this theta is inside the sine, this one's inside the cosine, that has to match the theta on the bottom. They have to be the same. So that's what we have here. All right, 5x is our theta on top, and so 5x is our theta on bottom. So this is exactly in the format we need it to be in. So we know that the answer is 1. All right, so we run into a problem when they're not the same. So that's what's happening here. We are still approaching 0, and we have our theta on the inside. We can't change what's on the inside of the trig function. That has to be what it is. This one is not theta because it's not the same as this up here. And we can change this. Okay, what's happening here is these are being multiplied together. So I can always multiply. If I have a fraction, I can always multiply by something on the top and something on the bottom. Okay, so that's something we're going to want. We want this number to be a 5 because we want it to match up with this. So let's multiply by a 5. We'll do that on top and bottom. All right, and then so what's happening down here on the bottom is everything's multiplied together. So we can apply the commutative property, which means I can rearrange these in any order that I want. So I'm going to rewrite this limit problem. The limit as x approaches 0 of sine of 5x multiplied by 5 divided by, and then I'm going to put the 5 over here. So that'll be 5x multiplied by 4. So I'm just flipping the 5 and the 4. Okay, and then this is a log property that we can apply here. The limit as x approaches 0 of sine of 5x over 5x. So I want to make that its own limit because I want to be able to apply my property. It's this exact problem that we just did. But then I'm going to multiply that by another limit. The limit as x approaches 0 of 5 over 4. All right, now we can apply the property here. I know that's equal to 1. And this is the limit of a constant, which is equal to that constant. 1 times 5 over 4 is 5 over 4. All right, another special thing about this sign property is that it applies if it's upside down as well. So I'm going to come back up here and put another equal sign, and we're going to say the limit as theta approaches 0 of theta on top divided by sine of theta on bottom. So if you have it upside down, the property still holds true. It's still equal to 1. So that's what we're going to use down here when we have this sine of 3x on the bottom. Okay, so let's figure out what we need to multiply by. And I'm actually going to multiply by a little bit more than I really have to, but I think this is a much clearer way of figuring out how to get what you need. So the 5 doesn't matter. I could pull the 5 out of the problem right now if I wanted to, because that's a constant. So I'm focused on the signs. Let's talk about the one on top. So this is sine of theta on top. Theta is 2x. So to be able to apply the property from up here, I need to have a 2x on the bottom. So I don't have one right now, which means I'm going to have to multiply by a 2x on bottom. I'm not allowed to just multiply on the bottom. I have to multiply on the top and bottom. So I have to multiply the top as well. All right, now I have a sine of 3x on the bottom. So if I'm going to apply the upside down version of the property, that means I need to have a 3x on top. I don't have a 3x on top, so I'm going to have to multiply by a 3x on top, which means I'm also going to have to multiply by a 3x on bottom. All right, now we're going to apply the commutative property. So the limit as x approaches 0, we still have our 5 on top. We have sine of 2x on bottom. And then I'm going to move this 2x over here. All right, I'm going to start this step over. So I'm going to erase this. Okay, so since everything's multiplied together, I can apply my limit property that says I can separate this into multiple limits. So I'm going to go ahead and do that now. Okay, so first thing I'm going to do is take this constant 5, and I'm just going to pull it out. That doesn't have to be inside the limit. All right, then I have the limit as x approaches 0. So I'm going to do the numerator as sine of 2x here. And that means I'm going to pull the 2x from the denominator here into that. Okay, if it helps, you can kind of lightly cross these out as we've used them. So we've used the 5, we've used that, we've used that. All right, then my next limit as x approaches 0. Now I'm going to take the sine of 3x from the bottom, and that means I'll need a 3x on top. So now I've used that and that. Okay, so I'm not quite done yet. I still have one more thing I haven't used, this 2x and that 3x. So that's the limit as x approaches 0 of 2x divided by 3x. All right, last thing to do is to evaluate all this. So this is equal to 5 times that is equal to 1. That's us applying the property. This is equal to 1. That's us applying the property. This, the x's will cancel. And now it's the limit of a constant, which is equal to that constant. Multiply that all together, and you get 10/3. All right, one thing the CAS calculator will do is limit problems like this. The CX will not do these as well. I don't know. The CX might do it. I would have to double check, but I know the CAS will do it. So I'm going to plug this one in the calculator just to show you. So I'm going to hit Control Doc. All right, so you can get limits from this menu. I call this the template button. So it's a button next to 9. You press in, a bunch of templates pop up. And one of those templates is limits, second from the end. Okay, so we can type in x approaching 0. There's a little spot here. We haven't gone over what that would be. So once we do, I'll tell you about it. All right, and so we have, I'm going to hit Control divided by, we have 5 sine of 2x. Then on the bottom, we have sine of 3x. And there you go. Evaluates to 10/3. All right. Next one, last one for this set of notes is the limit as x approaches 0. So there's our all-important 0 right there. Forgot to circle it on this problem. One thing I didn't do on the previous problems, which I probably should have done, is don't forget to always consider direct substitution. So it's not always going to be a part of a property, but you should try if you plug in. Remember, sine of 0 is always 0. So if I plug in 0, I get 0 over 0. Plug in 0, sine of 0 is 0 over 0. Okay, I have a sine of 0 over a sine of 0. So they're all 0 over 0. Same thing here. 2 times 0 is 0. Sine of 0 is 0. 0 plus 0 is 0. Then you get a 0 on the bottom. So these are all 0 over 0. So what we're doing is we're trying to rewrite our limits so we can apply that property that we've learned about, and then we can get our answer instead of our indeterminate form. Okay, so what's going to happen here is we are going to split this up. Anytime you see a monomial on the denominator and a polynomial on the top, you can use this as a common denominator and split it up at the plus sign. Okay, so that's what we're going to do. We're going to do the limit as x approaches 0 of 2x divided by x plus the limit as x approaches 0 of sine x divided by x. Okay, so this limit, the x's will cancel. Now we have the limit of a constant, which is equal to that constant. This limit, we're going to apply the property we just learned about, add those together, and you get your answer. All right, so that's using your trig identities. And I hope you enjoyed, and I'll see you on the next lesson.